Video, we're going to have an introduction to the normal distribution. Now, before we get to introducing the normal distribution, I want to introduce some new statistical notation. Here in this slide, I have some information about the sample in a population, right? Remember, your population is your larger group that you truly want to make inferences about or draw conclusions about. Normally, in research, we don't have the time, the resources, or it may not even be feasible to collect data on the entire population. And so we collect a subset of that population, usually through random means if we can, and we obtain our sample. From that sample, we measure individuals on our variables, and if that variable is quantitative, um, some possible sample values that we can calculate are the mean and the standard deviation. Well, any number that's calculated based off of information from your sample, those values are called statistics. And so when we calculate our sample mean, we use the notation M. Sometimes we can use the notation X bar to represent our sample mean, and our sample standard deviation was given by SD. Whenever we use a number to summarize data about our population, we call that a parameter, right? And so we hadn't talked about much about populations, which we are going to do in this module here. We want some of the statistical notation that aligns with values related to your population. So your population mean, and we usually use Greek letters, is given by this Greek letter here. It's called mu, M-U. And then our population standard deviation, we'll use the notation sigma. All right. So I wanted to get this notation here so that it won't be a little confusing when we get to some of our later slides throughout this module here. Before we get to actually using the mean mu and the standard deviation sigma, let's talk about density curves. A density curve is a smooth curve that actually represents the population distribution of a continuous variable, right? So this all applies to quantitative data. So we're going to leave those nominal and ordinal variables alone, and we'll focus on those interval and ratio variables, specifically those that are continuous. So let's say that we had an example where we collected a sample of individuals. We measured the number of hours or the amount of hours that they spent taking an exam. We can see that most of the students in this sample, most of them took between a half an hour and maybe 1.5 hours, while very few of these individuals in the sample spent 2 or more hours on that exam, right? In addition to that, we can use words like positively skewed, right? We have a longer tail to the right of that distribution. It's unimodal. There are multiple things that we can really say about this distribution here. But remember, we have our vertical axis as the frequency. We can find our mode or our peak. There's a lot of things that we can say about that distribution there. Well, if that distribution is very representative of our population, so if we really think that sample is extremely representative of our population, then it may have some insight as to what our population looks like, right? And so what we can do is we can overlay a smooth curve on that histogram, and that could be considered a density curve, right? So here's some things to note about density curves. The shape of density curves are going to resemble those of the shape of your histograms. You can think of them as smoothed out idealizations of histograms, but they're created slightly different. For instance, let's look at our vertical axis. For our histogram, our vertical axis here has the frequency. We've seen histograms before where the vertical axis may be a proportion or a percentage, right? Well, when we look at the density curve, which is this red graph here, our vertical axis is not going to have the proportions or the frequencies, all right? And the reason for this is that they're created differently in order to help us find proportions of data that covers certain values of our actual variable. So we're not going to read density curves in the same manner as we read, let's say, histograms or some of our other graphs that we had related to descriptive statistics. But the focus of these density curves is to find proportions of data that has certain values of this variable that we have on our horizontal axis. In order to find those proportion of observations, we must find the area under the curve over the specific range of values that we're interested in. All right. So these curves were created so that whatever shape it has, the total area under that curve equals 1, which represents 100% of that population. And if we want to know the actual proportion of observations that cover a certain range of values, we have to find the area under the curve covering those specific values. Now, this is based off of population information, right? And so it kind of makes sense that this area under the curve is going to equal 1 because it's going to represent 100% of your population, right? Because truth be told, most of the time we don't even know our size of our population. And so density curves gives us ways to find proportions of observations using areas under the curve. Now, there's one thing I also want to point out here. Notice I use this term here, proportion of observations or proportion of individuals within that population. We can also find the probability that our variable actually lies within an interval of values using the same methods that we're going to be using in the subsequent slides. So whether I say proportion of observations or the probability that a variable is going to, an observation is going to take on certain values, I'm going to use the same methods. So it says here in this density curve example, here we have the population density curve without that histogram for that last example that I just looked at. It says, what would we do if we wanted to find the proportion of the population that spent between 1 and 2 hours on the exam, right? So we have our population distribution here. And if we wanted to find the proportion, we have to find the area under the curve. 1, x equals 1 is here. X equals 2 is here. So I'll have to find the area under the curve between those two values. That would give me my proportion that we're looking for. Well, in order for us to do that, we actually need some calculus. Now, of course, calculus, there's integral calculus. There are multiple ways that you can find the area under the curve for different functions. We're not going to use calculus in this course. We're going to rely on technology to give us this area. But always remember, when we're looking at population density curves, we're looking at the area under the curve covering a certain range of values. That's what I'm wanting to hone in on in this section. Now, there is a special, very popular density curve known as the normal curve or the normal density curve. Here on the slide here, I have the normal distribution. All right. It is a distribution for quantitative variables, and specifically we want to use this for continuous quantitative variables. We've talked about the normal distribution before. We know that it is symmetric. That means it has a line of symmetry, and each side is a mirror image of the other. It is bell-shaped, so most of the observations are in the middle of the graph, and then there are fewer observations on the tail end of that distribution. The mean and the median are equal to each other. They're at the center, the line of symmetry. And when we're talking about graphs, in the same way that we did histograms, your mode is that peak of that distribution. And so in this case, we can say our mean, median, and our mode are equal to each other. And then another property about normal distributions is that there are many different bell shapes, right? Some bells are very tall and wide, or maybe tall and skinny, and then others may be a little shorter and wider, right? And so the shape of those normal distributions and where we locate them on an axis are dependent on two things. And those two things are those parameters that we went over on the first slide of this presentation. It says any normal distribution shape can be described by its mean mu and its standard deviation sigma, those two parameters we discussed earlier. So let's talk about it. The mean mu actually gives where that line of symmetry is, right? So what value does the line of symmetry hit that horizontal axis? That is going to be your mean. And so as I have graphed here, we see I have the line of symmetry here. So that value on our horizontal axis is our actual mean. And the same thing happens for this graph here. If you look at your normal distribution, it is a curve, right? It's bell-shaped, it's a curve. And sometimes this distribution curves upward, and other times it curves downward. And the way that that graph curves is actually related to the standard deviation. So our standard deviation sigma gives the distance from the line of symmetry to the inflection points, and it describes the spread or how wide or how narrow our normal distribution is going to be. Now, using some new terminology here is actually some calculus terminology. Inflection points. What does that mean? Well, I'm going to look at this normal distribution at the top. This distribution kind of curves where it's opening upward. And then somewhere in this area here, the normal distribution starts to open downward like that, opening downward. Then over here, it starts to open upward again. Well, the points where it changes from opening upward to downward and then from downward to upward, those are called inflection points. And so when I look at this first graph, we have two separate inflection points, right? And so if I go from the line of symmetry, which is in the middle, to that inflection point, that distance is one standard deviation. That also applies to the second graph of a normal distribution. The distance from the line of symmetry to one of the inflection points is considered a standard deviation. All right. And so that's going to give us how wide, because if our normal distribution is tall, the distance from the line of symmetry to the inflection point is going to be shorter compared to a shorter and wider distribution where that line of symmetry to the inflection point is going to be longer. So that's why we get the location and the shape of our normal distribution by those parameters, the mean and the standard deviation. Let's look at this example really quickly. It says, which normal distribution has the greater mean, right? Well, the mean is at the center. So all I need to know is where my line of symmetry hits my horizontal axis. And if I look at this normal distribution here, it hits it at 15 versus in graph B, it hits it at 12. 15, of course, is greater than 12. So curve A has the greater mean. Let's look at the standard deviation now. And for standard deviation, I don't necessarily have to look at a specific value. I can look at the spread. How wide are the normal distributions? Of course, graph A is much more narrow compared to the graph of the normal distribution B. And so that one's very widespread. So graph B has a greater standard deviation. All right. I want to go over some properties of normal distributions because we talked about z-scores and how some z-scores tell us that our observation is a usual observation. And then we said that some z-scores tell us that our observation is unusual. And I want to get to why that is. And one of the things that tells us that is some of the properties of the normal distribution. One of those properties is known as the empirical rule. Before we get to the empirical rule, I want to review some additional notation. Once we know that a variable is bell-shaped and symmetric, it has all of these features of a normal distribution, we can use this notation here. So the variable is our x. We've used this before when we were looking at those sums when calculating the standard deviation and calculating the sample mean and stuff like that. We use x to represent the observations of our variable, or the values of our variable in our sample. We can say that once we know that that variable follows a normal distribution, this means that x is distributed as a normal variable with a mean of mu and a standard deviation of sigma. And once we know the mean and the standard deviation, we can replace those values in that notation there, right? So x is distributed as a normal random variable with mean mu and standard deviation sigma. Now I can draw, once I know my mu and my sigma, I can draw my normal distribution, right? I know that the mean is right at the center. And if I go from my line of symmetry to my inflection point, that distance is one standard deviation, right? So notice here that this distance that I have representing my standard deviation, I've basically scaled my horizontal axis in that number of units, right? So here to here is one standard deviation, here to here is another standard deviation, so on. And the same thing on the left side there. Well, the empirical rule, it says it helps me get some information so that I can find the proportion of individuals that are between certain values. The empirical rule says that approximately 68% of the observations are within one standard deviation of our mean. So that means if my mean is in the center, right, and I want to be within one standard deviation of my mean, I can go one standard deviation above the mean. This value will be my mean plus 1 sigma. And I can go one standard deviation below the mean, and I'll get to mu minus sigma. So I know that the area from here all the way to here constitutes 68% approximately. So if I know this value and that value between those, I know that 68% of the observations of this normal distribution are going to be between those two values. All right, that gives me the area under the curve. So this gives us kind of a quick way to calculate some areas. This is not the entire empirical rule. There are actually three statements. The second statement is that approximately 95% of your observations are within two standard deviations of the mean. All right, now I've already gone one standard deviation above the mean. So if I go one more, I'm going to be upwards to two standard deviations, right? So I get to this point, which can be labeled as mu plus 2 sigma. And I can go another standard deviation below mu minus sigma. And that's going to get me to two standard deviations below the mean. So I know that the proportion of my observations from mu minus 2 sigma all the way to mu plus 2 sigma, which will be all of this area under the curve between those two values, that would be about 95% of my population. And then last but not least, we can do the same thing, go another standard deviation above and below those previous values on our scale of x. We'll get to 3 standard deviations, and that's 99.7% of our observations. All right. Now, we already know that the total area under that curve represents 100%, but the empirical rule stops at 99.7%. Now, I've used these values here. These are the traditional values that are used with the empirical rule. Your textbook uses these decimals here. 68.3 is between plus or minus 1 standard deviation from your mean, 95.4 between 2 standard deviations, and then 99.7 is between 3 standard deviations. All right. It gives us a way to calculate proportions of observations that are within our population distribution if it's normal. If the distribution is not normal, then we can't use this empirical rule. It only applies to your normal distributions. All right. Now, remember, I'm going to z-scores, and I want to get back to the point where we said, oh, if my z-score is between these two values, then these are considered usual values that I would expect. But if they're beyond certain values, we get unusual scores. And this comes from our standard normal distribution as well as our empirical rule. Let's talk about the standard normal distribution. The standard normal distribution is a normal distribution, but it's the specific normal distribution with a mean of 0 and a standard deviation of 1. All right. It's a standard normal distribution. And so what we're going to do is we're going to be able to convert any normal distribution, no matter what mean it has or whatever standard deviation it has, we'll convert it to a standard normal distribution by calculating z-scores or converting every single x to a z-score. So what that means is we're going to take our x, we're going to subtract from that our mean, and we're going to divide by our standard deviation. These words are the exact same words that we used last week, but we were doing descriptive statistics. We didn't, and so we use M instead of mu, and we use SD instead of sigma here. Well, now we're talking about population distributions, and now I'm using mu and sigma. If you may recall, we said that z-scores are standard scores, so it's a method of standardizing normal distributions. We standardize them in such a way that they represent the number of standard deviations observations are from the mean. So they're measured in standard deviation units. And then much like the notation that we use for any random variable x being normally distributed, our z-scores will be normally distributed with a mean of 0 and a standard deviation of 1. So there's that notation once again. All right. And so the value of having our standard normal distribution is that instead of having our axes and our normal distribution labeled in a way where we are in the original scale of the variable, where we're having everything in terms of mu and sigma, now we can have our axis labeled in terms of standard deviation units. Notice our mean is 0 standard deviations from itself. So I can relabel my mean with a 0 when I convert this to a z. This is 1 standard deviation above our mean. And so this is 1 standard deviation. If I'm going to be in standard deviation units, this is equivalent to a z-score of 1. This one is equivalent to a z-score of 2 because I'm 2 standard deviations above the mean, so on and so forth. And so if I combine this z-scale with the empirical rule that I used in the previous slide, that 95% of our observations are within 2 standard deviations from our mean, we're going to see where we ended up getting this picture here where we talked about values of z that are considered unusual scores, usual scores, unusual scores, and very unusual scores. Notice -2 to 2, that constitutes the middle 95% of our distribution. And so if an observation falls within -2 and 2, it constitutes the middle 95%. We're saying that middle 95% are usual observations. Anything beyond that 95%, so the 2.5% on either side, since our distribution is symmetric, those are going to be unusual or very unusual scores. That is why we came up with these values here for our z-scores. Now, we're using this as a rule of thumb. Some people use beyond 3 and -3 as unusual, but in general, you're going to see we're going to use that 95% very often. And in our field of education, we use that 95% most often. We're going to be using that middle 95%. So -2 to 2 are usual. Anything beyond that are considered unusual. All right, that's where that is from. Now, we're going to want to use our standard normal distribution more than just finding out whether an observation is usual or unusual, right? And so it says the standard normal distribution can be used to find the proportion of a population who falls within the interval of values on that quantitative variable. So I know that I said that we can use the empirical rule to find areas under the curve. Our empirical rule has limits. It is only restricted to being 1, 2, or 3 standard deviations from our mean. Well, in real life, an observation may be 1.5 standard deviations above the mean, or 0.35 standard deviations below the mean. The empirical rule is not going to help me find the areas there. And so what I'm going to do is I'm going to use the standard normal distribution and what it means to find proportions of normal distributions in order to help me answer a lot of questions that we may be interested in. An example of a question that we may be interested in is this one here. It says, find the proportion of students who scored less than 100 on a test if the distributions of scores is normally distributed with a mean equal to 115 and a standard deviation equal to 10. Okay, I want to find the proportion of students who score less than 100. Well, historically, what we would do if we were going to solve this problem is we'd first draw a normal distribution that applies to this context. It's going to have a line of symmetry of 115, and the standard deviation is going to be 10. All right. And so I've got a normal distribution drawn here. Notice in the center of this normal distribution is 115. And I'm counting or labeling my axis in units of 10, right? Got 125, 135, 145. That's 3 standard deviations above. And if I go 3 standard deviations below, I get to 105, 95, and then 85. 85 is 3 standard deviations below. I do have 75 labeled here. But this is the normal distribution. Now, I want to find the proportion of students who score less than 100. So notice here, I have this point labeled here. Well, a point plotted here. That is at 100. And so if I want to find the proportion who score less than 100, I've got to find the area under the curve for values of 100 or less. I'm going to shade that in this diagram here. This is the area that I want to find. All right. So that's the first thing that we usually do when we want to answer this question. The next thing we do is we convert that value 100 to a z-score. Remember our formula for a z-score? You take the value x, which is 100. You subtract from that the mean, which is 115. And then you divide by the standard deviation, which is 10. Well, when I could do that calculation, I get a negative 1.5. Notice z-scores may be positive or negative. They're going to be negative when that value is below the mean. Notice 115 is our mean, which is 115, and our value 100 is less than that mean, so we should get a negative z-score. If that value was above our mean, we would end up with a positive z-score. All right? So once we find our z-score, what we would usually do, and this is the historical thing, right? We would normally, once we have our z-score, we can adjust our graph. I'm sorry here. I redrew my graph, but now I'm looking at my standard normal distribution where my mean is 0 and my standard deviation is 1. So I'm counting by ones here. I plotted my value of my z-score obtained that corresponds to my value 100, which is negative 1.5, and I have my area under the curve that I'm interested in. And so this area comes from the standard normal distribution, which traditionally we will go to a table known as the standard normal distribution table to find this exact probability. I would go to that table, identify negative 1.5, and that table would tell me what that probability is. All right. And normally, as I stated before, we would have to use calculus. We don't want to use calculus. We could use that table. But now that we have technology, we're just going to rely on our statistical program, which is JASP in this course, to help us do that. Okay. Now, finding the actual proportion, we're going to use JASP, and we're going to have a lot more details about that during our next video. So stay tuned, and we'll open up JASP and do multiple examples so that we can see how we can actually find that proportion to answer that question. We'll see you in the next video.